is that we have multiple TRACE32 windows. I'll show you here 3 of them. And each GUI here is in charge for one core of our system, or for one set of cores. What is most times quite useful is synchronization. So for example, when you want to start, for example, your ARM application processor, you also want to start your DSP. And vice versa, when you stop your DSP, you want to start your ARM application processor. So what we support is so-called synchronization. We have 2 approaches. The first approach is in software, which is very general case. We support it for multiple chips, for single chip, multi-core, and you might have chip-specific hardware support, which allows you to do this in hardware. But how does this work? In general, each GUI interface has got a so-called intercore master and slave port. So each GUI here has this port. You can also describe them as publisher, subscriber. And what you can do is you can configure your GUI to propagate a signal, for example, a break signal, through the master interface to what I call here the synchronization bus. What you can do, for example, in the second GUI is you can configure the second GUI to listen on this synchronization bus via the slave interface and to react on these events. So if the first GUI sends a break event, the other GUI can also do a break event. What happened now? This GUI, this core, the ARM application processor changed from running to break to stop state because of a breakpoint, for example. And what we do is, by software, we synchronize this event through our synchronization interface with other GUIs. If it's supported in hardware, we will do it in hardware, otherwise it's software. We can also do the opposite way. So for example, if the middle GUI will start, we can also configure this GUI to propagate this event to the synchronization bus. And we can configure the other GUIs to listen with their slave interface on this event. So the other GUIs will also start. I press here go, the other GUIs will also start. How this is configured? Down here, again, our so-called target system dialog. The target system dialog shows you at each point of time your current setup within your debug box. So what I set up here is an AMP system with one Cortex-A9 core application processor and a TMS320C6XXX DSP. It's a TI DSP. And what is shown right here is the synchronization. To configure synchronization, you have got 2 possibilities. You can either use our sync window, which is also available via the scripting interface, or you can simply configure it by clicking here. What I've done here is I configured the first GUI to send, for example, the go event to the synchronization bus. And I configured it to send the break event on the synchronization bus. And I did something also for the slave interface. I said, don't listen on the slave interface, but listen on the break interface. For the TIs, you see this exactly mapping, master go, don't react on slave, here. Master break, slave break, M and S, listen on break with master and slave. On the DSP, I did it the opposite way. I said DSP listen as a slave for goes and listen and act as a sender as master for breaks. So when I will start my application processor, my DSP will also start. If you break your application processor, the DSP will also break, and vice versa, as I configured both as master and slave. Which cores you combine together is done via UDP IP. If it's on the same debug box, it's done in software on the debug box. If it's supported by hardware, we will shift it to the hardware onto the chip. This is also the reason why we need this chip and core information. So let's sum AMP debugging together. We have a multiple TRACE32 power view GUI concept. You have multiple GUIs for multiple cores within your chip or for your multiple chips. You can synchronize your debug session with the synchronization features. We take into account shared resources like, for example, trace and also the synchronization logic on the chip. And we support heterogeneous setups with multi-core and multi-chip at the same time. Next topic is SMP. When we talked about SMP, we said that all cores are of the same architecture. They are all in one single chip. They understand all the same instruction set. So in the last situation, we had an application processor from ARM and a DSP. These two cores are not compatible to each other. Now we have the situation that all cores are compatible. They have the same address bus, they have the same core architecture, the same register set. They are all the same. So what we do in SMP debugging is we assign all cores of our chip to a single GUI. Yeah? AMP, you had multiple GUIs for multiple cores. Now you have got a single GUI for multiple cores. Again, this is the snapshot of the T32 Start tool. I've got a power debug interface too, connected via USB, and I've got a single ARM debug session. And this single ARM debug session will be responsible for all cores. So what you do in the SMP session is you select your multiprocessing core, a multiprocessing capable core. You can either, I've done this here for you, an Cortex A9 MP core. From the architecture of the core, we know the following. It supports up to 4 cores in one chip. So what happens in the system config dialog, you have got a parameter core number. This core number is automatically set to 4. This means that you can use with this Cortex i9 MP core up to 4 cores in one chip. But right now they are not yet configured, because your operating system could only use 2 cores of 2 Cortex i9 cores together, or your chip might only have 2 of them. And by the core number option, you select the number of cores you're going to debug with this debug session. So you don't need to configure it from the TRACE32 Start. You simply start your ARM debugger executable, and you tell us how many cores of your chip will be now combined together. Finally, we have still one single GUI. We get in the status bar of the GUI, we get a so-called core selector. This core selector tells me here the situation where I configured all 4 cores to be debugged with this single GUI. So in the status bar, we have this core selector. 0, 1, 2, 3, so 4 cores. When you change the core down here, simply by clicking, the register contents of the register contents, the data contents, will change. We assist you by colors. I've got configured here that the red color stands for core 0 and the green color stands for core 1. This is automatically done by TRACE32 PowerView. Simply by clicking here, you will see the register contents of your first core. By selecting the second core, you will see the register contents of the second core. The same happens for the list windows. For example, the program counter will will be definitely be different from between the cores. So also the list windows will change. What you also might want to do is you want to inspect concurrently the status of the first core, the second core, the third core. You can do this also. Each window, which is core dependent, for example, the register view, data list, data dump, peripherals, will get an option to select a specific core. So this window, register/core 0, is now fixed to the first core. It will be no longer depend on the core selector down here. When you want to debug your system, you're using breakpoints. And when you're running an operating system, you don't know, or you might don't know, where your task will be started. Remember again, we have multiple cores in one chip. We have a single operating system, and a single operating system is in charge to assign tasks to cores. You don't know whether your task will be started on the first core or the third one. So in case of a break event or a trigger event, we will automatically select down here the core which triggered the break event. So we will automatically switch the windows to the core of interest. In AMP setups, we also talked about synchronization. Synchronization for SMP systems is not optional, it's a necessity. The operating system expects that all cores at each point of time run synchronous. For example, in an SMP system, you stop your first core, the other three go on running, they will perhaps no longer receive any task, and your time slices will be simply corrupted. So SMP systems are always run synchronous. So if you use a step on one core view, both cores, this one and this one, will step. If you use and go, first core as well as the second core will start. All cores. For SMP systems, you have always hardware support, which means this go and step will be synchronized in hardware and also break events. Okay, so let's sum this together. SMP, with SMP debugging, synchronous multiprocessing, we have a single TRACE32 power view GUI concept. You have got a single window which will control all cores of your system. You have a concurrent display of all CPU states. The synchronization don't need to be set up. It is ensured all the time. And we also support OS awareness. You will hear later here from my colleague, Mr. Jamal, for SMP. So we also support, for example, Linux operating system, which controls 4 CPUs. You can also see a setup like this on the outside at the Q&A desk. So let's get a bit more ARM specific. ARM features the so-called core site architecture. Core site is a collection of is a specification of debugging. It includes memory accesses, cross-trigger between CPUs, that all cores can be started and stopped synchronously, so it's done in hardware. And it defines also shared resources like the trace. A simplified example for a core site featured core is, for example, a TI OMAP 4430. This is a very much simplified model. The CPU is much bigger. In this single chip, I have two Cortex A9 cores and a DSP. So in the lower half of the picture, you see the CPU part. This is the part you see from the software side. You have two Cortex i9 cores connected to a shared bus, and you have got a DSP, which is also connected here to the shared bus. From the debug point of view, the ARM cores are connected via, not directly connected to the JTAG. They communicate indirectly via this debug access port. This debug access port will then communicate with the single cores, and it might also send events to both cores. The advantage of the debug access port is, for example, when you send both cores to power saving mode, you can still communicate with the chip via the debug access port, and you still have got access to the bus, which is a quite nice feature. So here again we have on the upper half the chain. We connect our debugger to the left, to the right. We communicate in this chain via the debug access port with the Cortex-A9 cores and via a classical tab controller with the DSP. What we want to do now is we set up the following session. We combine both Cortex-A9 cores in an SMP session, and we will use the DSP together with this SMP session in an AMP setup. So how is this done? You still configure your T32 Start configuration. Similar to the AMP case, I've got an ARM debugger assigned to my power debug interface and a DSP debugger assigned to my power debug interface. The first GUI will be later assigned to both Cortex-A9 cores. The second GUI, the slave debugger, will be later assigned to the DSP. So we start again with the master debugger. In the master debugger, we select our CPU, the OMAP 4430. By selecting this CPU, we automatically know that the OMAP 4430 has got two Cortex-A9 cores. So we can select them by core number 2. We say, with this command, again, the operating system is going to use both cores in an SMP setup. So we are still on this side in the picture, and we connect to our system. The next step is we need to set up the chip. The Cortex-A9 cores of the OMAP 4430 are in charge to initialize the system. So what we need to do is we need to enable the slave cores, in this case the DSP. It's clock gated, powered down, and held and reset. This is highly chip specific, and you'd also need to do this in the code. So when we set up the master session and release the second core out of reset, we can start DSP GUI. And here we now do the same. We select the OMAP 4430 codename Tesla, which is the DSP of our SoC. And what we need to configure next is the core setup. Remember, we have got a single chip and it's the third core. Why? First core, single chip, first core. First chip, second core. First chip, DSP is the third core in this chip. Why are we not able to reconfigure this? Classically, multi-core debugging was with multiple chips, so we increased automatically the chip number. Today, it's mostly that we need to increase the core number, but we are compatible to the old way, so you need to do this on your own. And finally, you connect to your DSP, and you can then go on with synchronization and synchronize the Cortex-A9 cores with the DSP. As we know the core setup, we know that the ARM cores are in the same chip. Then with the DSP, we can use the cross-trigger matrix module, which is in the ARM SoC. So we will hardware-based synchronization between the DSP and the CPU. And voila, again the target system window. We set up an OMAP 4430 SMP session using two Cortex-A9 cores and a TMS320C6XXX DSP debugger. The upper half shows the ARM side, and the lower half is the second GUI, is the DSP side. So let's sum this all together. what we have learned today, SMP debugging means we have the same core architecture for all cores of our single chip. All cores share their code and data. They run on a single operating system, which also implies they have a single task set, which is shared among all cores. For debugging, code debugging point of view, they share also their debug symbols. They have got only a single code file, a single ELF file, or single symbol file you will load onto the system. SMP debugging is synchronous by design, and we have the same GUI, we have the same common TRACE32 user interface, and got a single window for all cores. For all cores, again, we have a single window with the core selector down here. In the AMP case, we might have different cores. They might be in multiple chips, they might have multiple operating systems, multiple task sets. We have designated debug symbols. Our ARM application processor code is not compatible with ESP code, so we have multiple symbol files. AMP is asynchronous by design. You have the same common user interface, but you have got multiple windows. For each core or each set of cores, you have got a single window. You have got one window. Our solution for you is you only need a single debug hardware box to debug all cores in your system. You can use SMP and AMP setups simultaneously with a single hardware box, a single debug cable, and a single debug connector on your printed circuit board. You have the uniform user interface, TRACE32 Power View, which you can use for all cores, regardless of the architecture for your system. And we support right now more than 70 core architectures, so it's quite likely that we can cover also your situation.